this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. So this time we're continuing our exploration of the sun and the sun itself and looking at exactly what powers the sun and what makes it go. Last time we looked at thermodynamic equilibrium, we looked at hydrostatic equilibrium, and we learned that thermodynamic equilibrium leads to internal structure of the sun, and all these equations dictate that, where some locations inside the sun are convective and some are radiative, meaning that's how energy is transported. And which one dominates, whether it's radiative or convective, depends on the density and temperature and pressure at that location. And so the equations themselves dictate the internal structure. And the fact that the sun is emitting light and is emitting energy means that it must be changing. So how exactly is it changing? How long has it been alive? That's going to be the question for us today. So really, we're talking about energy production in the core of the sun. We're looking at that last equation from the stellar structure equations, little dl, how much in a little onion-sized shell around the center, how much luminosity, dl, is produced in a little shell of radius dr at a distance dr, r squared, r, and with the matter density of rho, which is that little p, and epsilon e is the total amount of radiative luminous energy, and E sub nu is the stuff that escapes by neutrinos. What's being lost? What's being seen? How do we get light from the sun, and how long has it been doing this? All right, big question. How long can the sun glow or shine or emit light? How long has it been doing it? How long can it do it? What is this lifespan of the sun? It's a really important question because it has bearings on pretty much everything else in the entire solar system, including evolution of life on Earth. So, in order to know how long the sun has been glowing, shining, and emitting light, we've got to know two things. We have to know how much internal heat is there in the sun, and how fast is that heat lost per second as sunlight. Well, the second one is simply the luminosity, and we can measure that relatively easily. It's really tricky to understand exactly what we mean by internal heat, though. So internal heat is a lot of different things. How can you get heat? Is it just simply hot and that just simply emits the heat? Is there some process that creates heat? And then that heat can be then transformed into light by various physical processes, and then that eventually makes its way to the surface and it gets lost. We saw last time that the process of light transmitting through the radiative zones actually takes about 250,000 years to get out from the core. That's how dense it is down there in the core, that it takes an extraordinarily long time for it to get out. But 250,000 years is a long time, so how old's the Earth and all that kind of stuff, and that's bearing upon this subject. So let's actually go back to the early part in the 1800s when people were developing the concepts of thermodynamics and such things, because steam engines were being built, combustion engines were being built, and so there was a massive study going on all across Europe and the Americas about exactly how thermodynamics worked and how heat interrelated with work. And that's everything we really want to know. So by the end of in the early 19th century and by the late 19th century and the early 20th century, way up to the latter part of the 1900s, or the latter part of the 1900s, there are pretty much two ways that things could have sources of energy. One is chemical energy. You either burn something or you blow things up. And so that was fast oxidation of materials, or you put something on top of a hill and let it roll down that hill, which is gravitational potential energy, or you whack it with something. You take two things that are really far apart and let gravity pull them together, and then you make a big boom, and that would be like a meteorite hitting. So essentially, those are your two major energy sources that were known. And if you look at the economies and what people did back in the 19th century in order to do that, pretty much everything was reliant upon that. The electricity itself had not been developed until as a viable option for a very, very long time. So basically, burn stuff, blow stuff up, or drop things off hills. And that's how bread was made in water mills, because as a river would go by, that would turn a paddle, and that paddle would then turn a grindstone. And rather than make horses do it, you make the water going by a river do it. And so bakers used to be right by and smithies, or using whoever needed power, steady, reliable power, would put a mill right on the waterfront of a river. Anyway, so that was what internal heat could be supplied in the 19th century. And people at the same time, other scientists at the same time, were studying how old the Earth was. And this was a fascinating study. And people were looking at how the Alps were overturned and folded, and the rocks were folded, and then the uplifted rocks in the Rocky Mountains in the American West. And even in Manhattan, if you go around the island of Manhattan, you find up in the northern areas, you see that the rocks are tilted and they're layered and tilted. So things have been moved. And if you look at layered sediments, such as sandstones or where fossils exist. But most classically, as one of the great things, is the beginning of geology is by Jim Hutton in Scotland, and he hung off of a cliff above the ocean called Sycamore Point in Scotland. And what Jim Hutton did is he looked at all the layers and found that inside the layers, just off this coast, this place called Sycamore Point, he found that there were rocks that had been laid down by lava, then rotated, and then covered in sediment, then worn down, and then lifted straight out of the ocean hundreds of feet. And that process must have taken thousands upon thousands of years. And basically, these inclined rocks that occurred everywhere, and were there because of geologic processes, because nobody at the time was saying, okay, let's be logical about this. People didn't do this. Aliens or demons or devils or gods didn't do this, because that's boring. And to actually say, well, these creatures came down and gave us this weird look to the Earth, it's kind of silly, because that's, in a theologic sense, it's not that silly because that's the nature of creation, but in a geologic sense, actually trying to understand it, you would come up against the idea of, well, okay, I can't prove that aliens came here or giant lizard people came and rooted around in the rocks and did that. So let's actually try to get a physical solution that makes sense, that keeps it simple, that we can justify. And that's called science. Everything else is either called theology, mysticism, or metaphysics. The problem is that when we looked at the age of things, it was found that the age of the sun was only about, if you think about chemical reactions, only keep the sun shining for a few thousand years. And if you whack the sun with a huge amount of meteorites, that keeps it going for almost 1,000,000 years. But so if you even imagine that every now and then the sun gets hit by something the size of Jupiter or something, then the sun could last a few million years. But geologists are finding that the Earth had to be hundreds of millions of years old, if not billions. So there was a fundamental conflict that was developing in the 1800s about how old the Earth was. And most geologists were saying, well, the Earth is older than the sun. And physicists who were, very smart, said, no, you geologists must be wrong. You're just looking at rocks. We're thinking thoughts. So this was pretty much the attitude that happened in the time, and there was a definite lack of reconciliation because one group sat around and thought deep thoughts in big places, and other people went stomping around in the Alps. So, in the 1800s, two physicists, Lord Kelvin and von Helmholtz, developed an idea by which the sun could turn gravitational potential energy into light. So if you start with the sun, as we did in the previous lectures, in hydrostatic equilibrium, and with the internal pressure balancing the gravity, meaning it's hot enough in the center that gravity can't compress it, you then say, well, okay, fine. The light from the sun is luminosity, and that's radiated away, and it takes away some of the the sun's internal heat, which means that as the heat goes, it gets cooler inside the sun. And since it gets cooler, that allows it to compress, because a cool gas, if you take a hot gas and cool it, it compresses. So now it's got a lower internal pressure, which allows it to compress, which means the sun itself contracts and gets smaller physically. It's not just a big thing, it gets actually physically smaller, the radius gets smaller. And so then when the gravitation contraction compresses the sun, it then heats back up until it gets to balance position, and so it balances itself out, and the outward pressure increases because it's hotter now deep in the core, and then hydrostatic equilibrium is then reestablished. And this cycle then repeats, and the sun gets smaller and smaller by about 32 meters per year. 32 meters per year. Wow, that's actually kind of it's an interesting and very quick compression. which leads to the sun only living for maybe 10 or 20 million years as its maximum. But this is called the Kelvin-Helmholtz mechanism for producing energy or producing light out of gravitational contraction. Basically turning heat into light, and you heat something up until it glows. And that's where the heat and light comes from, because you assume, as Kelvin and Helmholtz did, that all the heat gets converted into black body radiation, and all the energy of photons and light becomes unified inside of the sun because the sun's opaque. And since it's opaque, the light bounces around inside of the sun until it has the same temperature as the material, and the material and the light have the same temperature, so therefore it is a black body radiation, which is what is observed. So how long does it take? So you can't glow and contract forever, and if it does power that, then we can assume that the gravitational potential energy, which is the gm subsun squared over r squared, over r, this r of subsun. So this is the total amount of gravitational potential energy if you take all of the matter of the sun and spread it out to infinity, way out, and then just say, okay, now let's take all of this matter, pretend it was at infinity, and let it all fall together to form the sun. And so as it falls together, it loses energy. And that total amount of energy it can lose, going from infinity to as small a point as you like, is the gravitational potential energy. Take the current gravitational potential energy, which is the numerator of that equation, and divide it by the luminosity, the current luminosity of the sun, L sub sun. And that's the energy emitted per second. So this ratio says that the sun could only live for about 30 million years, which is nothing, which is really nothing. Very, very, very short time scale. But this is important for stellar, but if you think about it, this might be important for stellar formation, but not necessarily for keeping the sun alive forever. If this is the only thing that the sun or any star ever did, then stars could only live tens of millions or hundreds of millions of years at the most. So by the late 1800s, Kelvin and Helmholtz basically take a couple extra things. As the sun will shine for a little over 20 or 30 million years. And that it was even actually corroborated by Kelvin, because he went and looked at studies done at the difference in temperature between the surface of the Earth, rocks at the surface of the Earth, and rocks deep in mines. And he assumed that the Earth was once completely molten. And if the Earth was once completely molten and cooled to its present temperature inside, he got an age of about 10 or 20 million years. And he said, it's a good estimate, so I'm on the right track. So the Earth's only a few tens of million years old. But geologists were saying, no, it's a lot older than that. It's about 2 or so billion years old. Kelvin and Helmholtz, from their high seat in academia wearing wonderful clothing, said, geologists are wrong. Nature says, you guys are wrong. And geologists said, getting outside is nice because, nice day. Get out of that place and go walk in the Alps and go look at the rocks. The problem is that not all of the physical processes that nature did were known to Kelvin and Helmholtz at the time. They needed to be discovered. So let's take a second back and just say, let's take one of the great things that happened in the latter part of the 19th century, and that is the great industrial revolution, because of the discovery and the use of coal-powered burning all across Europe. And let's pretend for a second that we've got a coal-powered sun. So if you burn a kilogram of just regular old brown coal, that's about 25 megajoules of energy. Remember, 1 joule per second is 1 watt. So this is about 25 megawatts. If you burned 1 kilogram of coal in 1 second, you would get 25 megawatts. So that's a lot of energy. And we have coal plants across the country and across the world because it does release a lot of energy. However, the sun's luminosity is a little bit brighter. It's about 4 times 10 to the 26 joules per second, or 4 times 10 to the 26 watts. And at a total amount of 25 megajoules per kilogram, you'd have to burn up almost 2 times 10 to the 19th kilograms of coal every second just to keep up with the sun's luminosity, if the sun is powered by coal. Now, since the Earth has a mass of 6 times 10 to the 24th kilograms, at that rate, you would burn an Earth-sized ball of coal in about 4 days and 8 hours. Now remember, about 1 million Earths fit inside the sun, so the mass of the sun is about 1 million times that of the Earth, so that gives you only about 4,000 years. Wait a second, that matches what those creationists are saying the age of the Earth is. Maybe they're right about something there. I don't know. But, don't tell them that because they might glom onto it. Anyway, just go talk to creationists and tell them that the coal could power the sun. That makes it only 4,000 years old. You'll have a lot of fun. Troll them massively if you wish. In any event, 4,000 years is the length that you get if you want to have a coal-powered sun, and it doesn't work because everything that we know makes the Earth much older than a few thousand years. Okay, back in 1896, Henri Becquerel was on the forefront of research, and in 1895, Wilhelm Röntgen had discovered X-rays. And what he'd done by looking at naturally fluorescent materials and minerals. So Becquerel was investigating these fluorescent minerals, meaning something made out of uranium. If you take pitchblende and you compress it, it emits light. So these are fluorescent minerals that he thought were glowing because they were irradiated by the sun. And so what he did is he thought, well, it must be getting light from the sun and converting it into this light, so it must be sunlight that's doing it. So what he did is he was going to go outside and take a whole bunch of photographic plates with potassium uranyl sulfate and wrapped it with black paper. And he was going to expose them to the sun and then go and see what was done and see what the images were. So he put something like a ring or some images on there to see what would be imaged on the sun. Unfortunately, the day he was going to do that, it was cloudy that day, and so he left it all wrapped up, and he went, oh, darn it, my photographic plates are ruined because it was a cloudy day. Kind of funny, because he wanted to expose it to the sun. But he left them wrapped in black paper, and he said, oh, what the heck, I'll expose them anyway. And even though they hadn't been exposed to the sun, he found that there were images of the objects that he had placed in with the black paper. And so therefore, the uranium itself had emitted radiation without any external source of energy like the sun or dropping rocks on top of it or like coal burning or something weird. So therefore, Becquerel discovered radioactivity. He discovered that a mineral actually emits light. So what he did then is he made an apparatus very similar, and people had learned a long time ago that there were different kinds of emissions from these objects, and this was the forefront of research in the latter part of the 19th century, is if you take a charged plate with a plus or minus on charged plate, or a strong magnetic field, and then you take your sample that's radioactive, and you put it inside a lead container so it all comes out a particular hole, and then you have a charged plate with a strong voltage, or you have a magnetic field. The alpha rays, which are positively charged nuclei, helium nuclei, they will bend towards the negatively charged plate in their path. And so they will veer off to the, up in this direction. And if they're beta rays, they're electrons. And so they will be attracted towards the positively charged plate. Notice how the alpha rays, though, go farther than the beta rays. And that's because alpha rays are helium nuclei. And as helium nuclei, they're made up of 2 protons and 2 neutrons, so they don't get affected as much. So their path is not changed. However, electrons are very, very light, much lighter than helium nuclei, so their path gets bent rather rapidly. Gamma rays, though, don't get bent by it. So what was discovered is that alpha rays are positively charged, beta rays are negatively charged, and gamma rays are not charged. And so they had these 3 different kinds of things, and they were based upon their electric charge. And this was part of the great discoveries of the latter part of the 19th century. All right, 1905, Einstein had his great year, and he published special relativity. And he found that mass and energy and special relativity are the same thing. And that's through the great equation E equals mc squared. And it says that it's possible to somehow transform matter to energy and energy to matter. And he basically said they're the same thing, and that's the nature of one of the discoveries of special relativity. So if you can somehow have a way of actually converting matter directly into energy or energy directly into matter, you can do this. So there's an equivalent amount of energy that resides in every piece of matter that it can be released to this large amount by multiplying it by c squared to get you the total amount of energy that's stored in the matter if it is converted completely into energy. That's what that means. So 1920, Sir Arthur Eddington examined someone else's previous measurements, F.W. Aston's measurements. Aston was measuring low mass elements like hydrogen, helium, lithium, beryllium, and so forth. And he noted that and Eddington noted that 4 protons have just as has 0.7% of more mass than a single helium nucleus. So it's kind of funny because helium nuclei are 2 protons and 2 neutrons. But 4 protons have a little bit more mass than that. But a neutron's a little bit less, a little bit more massive than a proton. So what's going on that these things are actually, that a helium nucleus has less mass? So we said, let's say, do we take the Einstein's E equals mc squared, and he proposed then, let's take 4 protons, put them into one helium nucleus, and the remaining 0.7%, less than 1% of the mass, could be converted into energy. So Eddington said, well, what if you did this? If you converted it, then you'd have that. And he said that's a heck of a lot of energy, because if you take that if you have 1 gram of hydrogen, 1 gram, which is equivalent to the weight of a paper clip. In the internet era, well, there's no such thing as paper clips anymore in the internet era, so what? That might be a couple, like a sheet of paper or something, or half a sheet of paper is about 1 gram. So, paper, goodness, what? People even know what paper is because nobody does paper. Well, anyway, grams. A few receipts that you have to take when you go and use Apple Pay at a store or something. Anyway, 1 gram of hydrogen, if you convert it to helium, 0.07 or 7 milligrams is converted into energy, and that becomes 6 times 10 to the 11th joules. And now that's a lot of energy. That's so much energy you could lift 64,000 tons of rock to a height of 1 kilometer. That's how much energy you could do with that. So that is an incredibly explosive amount of energy that comes out of 1 gram of hydrogen. So Eddington said, well, this is a huge amount of energy. Maybe we can use this. And that was his publication called The Internal Constitution of Stars on October 20th of 1920. However, it wasn't accepted because one does not simply fuse 4 protons into a helium nucleus. And so how do you actually do that? There's really hard to do. 4 protons colliding at once is extremely unlikely. It was also shown that 2 protons together aren't stable because, well, they both have positive charged nuclei. So how do you get 2 things just to stick? And somehow, well, even if you do chance to get 4 protons together, somehow you got to turn 2 of the protons into neutrons. Where does that happen? And it's got to be extraordinarily hot with temperatures greater than 10 billion Kelvin to get them close enough to fuse together. So that's the 64,000 ton question. Well, actually 4 aspects to this. And so how do you fuse 4 hydrogen nuclei into a helium nucleus? And that notation that we see at the top there, the hydrogen nucleus, when we say 1 to the upper left, that means how many total numbers of particles there are in the nucleus. And then a 1H means it's just a proton. But 4He means 2 protons and 2 neutrons for a total of 4 particles. Whenever it says helium, it always means 2 protons. Now you can have 1 less neutron, so you can have helium-3, and you could even posit helium-5, but I believe that's extraordinarily unstable and doesn't exist in nature, as well as helium-2, which doesn't have any neutrons, which also doesn't exist in nature. So this is a very difficult thing to do. So let's look at the first thing. Trying to make them collide and stick is very tough. Why? Because 2 protons have an electrostatic repulsion. They are positive charges, so they repel. Like charges repel, opposites attract, just like that old Janet Jackson song, right? So electrostatic repulsion is so great that the temperature is so incredibly high that nothing can happen. So what do these 3 equations say? The U sub 2, 1 means let's take 2 protons, number 1 and number 2, that each have a charge Q. And Q is the electrostatic charge on a proton. The Q1 is the electrostatic charge on proton 1, and Q2 is the electrostatic charge on Q2. And D is their distance between them. Let's say it gets down to as close as 10 to the minus 15th meters. Let's say that's our D for distance. The 1 over 4 pi epsilon sub naught is just the way we convert charge and distance into potential energy, and that's what the U sub 21 is the potential energy of taking 2 protons, number 1 and number 2, and bringing them to a distance of 10 to the minus 15th meters from infinity. How much energy is created by that? What is the potential energy of them pushing apart? It's a pretty big energy. So then let's say, we can then say what a kinetic energy is, and we say, well, imagine that what we want to do is we want to get the kinetic energy high enough such that they can get to that potential energy, so that all of the potential energy is converted into kinetic energy. And what would the speed have to be of a proton in order for it to get that close? And that gives us a speed, a kinetic energy. And if we set that, if we say, well, that's the kinetic energy we wish to have, we find this an extremely fast pace. It's a very, very, very high speed. But then we want to actually say, well, if we convert then the potential energy into thermal energy, because thermal energy is a representation of the speeds of the particles, we then set the potential energy, U sub 2, 1, to the thermal energy of the gas. And so we'd say, well, what would the average temperature of all these protons have to be in order for them to get as close, to have the capacity to get as close as 10 to the minus 15th meters? And that ends up to be about 10 billion degrees, or 10 billion Kelvin, which is a pretty high number. And it didn't seem like at the time that anything could actually get them that close. So back in the early 20s, people thought, well, the temperature of the sun has to be on the order of 10 million degrees Kelvin, 10 million Kelvin, not 10 billion. So it's 1,000 times cooler than it needs to be. Well, George Gamow, who is pictured here, he's in his striking suit, was researching exactly, in 1928, was researching how subatomic particles escape from the nuclei of atoms, because, well, the discovery of radioactivity said we have alpha particles flying out, we have beta particles flying out, and they said, well, how do they get out of those nuclei? How do they leave the nuclei? So people understood that nuclei were being broken down and becoming lighter, so therefore chunks were missing. And they said, wow, there's a huge amount of energy that's coming out from these things. How do they get that energy, and how are they getting it, and where are they going? So they discovered that the amount of binding energy of a nucleus was extraordinarily large. In fact, it was too large for any random process to just say, now I'm out and gone. There was no classical way for things to bounce around inside the nucleus of an atom, thinking of it as like a hole in the ground, for them to bounce around laterally such that they bounce around enough that they would pop out. So quantum mechanics comes to the rescue. And Gamow uses the recent ideas of quantum mechanics, which states that all particles are also waves and have a distinct wavelength. We can imagine that the barrier to get out is a finite one, meaning it has to have a certain amount of energy and has a certain barrier to leave the nucleus. And whatever that barrier is, we can approximate it by some block. And we'd say, imagine that the wave of the waveform of the alpha particle, for a brief moment, gets outside of the barrier, and just on the chance. So sometimes it whacks the barrier and it reflects off of it, and maybe some of the wave goes outside. But imagine if the entire wave, on the off chance, goes outside the barrier. Because it's a wave, it must be continuous. So if it does that, then it escapes. So that's called quantum tunneling. And quantum tunneling says there's an off chance probability, a distinct probability, that it just simply goes past the barrier, which cannot happen in classical physics, but it can in quantum mechanics. And this idea allowed him to say, well, this is how things leave nuclei, and it worked. So then in 1929, just a year later, there was a couple of students, other researchers, Robert Deckard Atkinson and Fritz Houtermans, said, try to put it in the other direction. See if you can do it by putting protons together with protons. And they found that using the concept of quantum tunneling, you can actually have them merge together to form the nucleus that is formed of a proton and a proton. They can get them that close together at the lower temperatures that are known, the 10 million Kelvin, not the 10 billion Kelvin, using quantum tunneling. However, that was still an unstable nucleus of 2 protons. So that was good, but it's not the complete story. Well, and this is what we call the Gamow Peak, which is a very important thing. And this is what he was talking about, and this is what the other two were talking about, which are talking about Gamow and Atkinson and Houtermans were talking about, is that the Maxwellian distribution of the probability at the temperatures that we're talking about, say 10 million Kelvin, the probability that a proton has that energy is the red dash that's falling from the upper left down to the lower right. And so the higher the energy, the lower the probability it has that energy. That makes sense, because it takes the highest energy things are rare. So the Maxwellian distribution is what you expect to have for a particular temperature when the protons are at that temperature. Some are high, some have higher energy and some have lower energy. They don't have exactly the same energy. There's a distribution. But very, very, very high energies are extremely rare. However, with higher and higher energies, the probability of actually penetrating the quantum tunneling barrier increases, and that's what the curve going to that increases to the right says. The higher the energy, the higher the chance that you actually get inside and stay. And so if you merge these two curves, you get what's called the Gamow Peak, which means at a particular temperature, for a particular certain energies of protons can actually get in, and that they're roughly around 4 kT, which is the time, roughly 4 times the temperature, 4 times the Boltzmann constant. So it's going to be a very, very high temperature, but the probability that this happens is still extremely low. But it just shows that there is a merging place where there is an overlap between the probability that they get through that barrier, which is the penetration probability, and the actual distribution of energies inside of the protons, inside of a thermalized protons field. So there is a chance, and that's called the Gamow Peak, and that chance is really tiny, but it's there. So how often do they actually get there? How tiny is that chance? Okay. So at the temperatures and densities in the sun, and you can actually calculate it out, you find that a proton, as it's whizzing around at the temperatures of 10 or so or 15 million Kelvin, goes about 3 millimeters before it collides with another proton. It's a very short distance. And they do that every 5 nanoseconds or so. So a typical one collides almost 200 million times every second. A proton goes 3 millimeters and whacks into the proton 200 million times every second in the center of the sun. A typical proton. There's a lot of protons in the center of the sun, so how often does this happen? Well, that's still not enough, because the Gamow Peak is very tiny. So it's still so rare that it's got to do 10 to the 25th collisions before it has, on average, before it has the chance to tunnel into the other proton and do the fusion dance. So it's an extraordinarily rare thing, and it's extremely temperature dependent. And if you push the temperature a little higher, then you get more and more and more, the penetration gets deeper and deeper. So that's pretty good. So quantum tunneling is extraordinarily rare, but at the temperature we're talking about, at 10 million Kelvin. But it's just enough to provide what's needed. And let's see how that happens. So what happens when they finally do stick? Okay, great. So now we've got a mechanism by which we can say they finally can stick. So nuclear fusion says that like charged nuclei got to get close enough in order to fuse, and they've got to be at this temperature, and they've got to have quantum tunneling. So let's see what we got. Let's say they get close and we got some quantum tunneling going on and protons smack together. So we got a proton smacking together, we got the little flash of light, and so what happens? Well, a whole bunch of stuff flies out. And we've got a neutrino flying out, a positron flying out, and a deuterium atom, or a deuteron, not atom, but a nuclei flies out. And the existence of the positron, the existence of the neutrino, and the existence of the deuterium nucleus had to wait until later until it was actually confirmed. But let's see what we get. So a positron is an anti-electron, and that basically is the same thing as an electron with a positive charge. And if you look up what Richard Feynman says, you could actually even look at it as a positron as an electron going backwards in time, or a time-reflected electron. And that'll send you down a rabbit hole on the internet. But for our purposes, it is the same exact mass and it has an opposite charge. And every aspect about a positron is the opposite of an electron. So when an electron and a positron meet, they annihilate. All of the energy, all of the matter that was the positron and the electron is converted into energy, and that energy is in the form of light, and that light is in the form of a pair of gamma rays. So it goes, because that two need to come out because of momentum concerns, but there you have it. So you have a gamma ray that comes out, and so you've got light in the form of gamma rays of high energy photons, and those photons bounce around inside there and eventually scatter and reduce and break apart and become lower energy by the time they reach the surface. So that's a beginning for how light can be created inside the center of the sun. So let's look at another thing, a neutrino. Neutrinos don't interact with anything. They just go foop out of the sun. As soon as they're created, they leave the sun. They just don't interact with anything. They are neutral. They don't do anything. They're gone. And the last thing is the deuterium nucleus. So a deuterium nucleus is basically a heavy proton. So you take a proton and slap a neutron on it. And so now the neutron itself, the deuteron or deuterium nucleus, the symbol could also be called 2H because it's one proton, but there's two nuclei, two atomic particles in the nucleus, so it would be a 2H. You can also call it a D if you wish. So the next step then is to smack a deuterium nucleus onto a proton, and we've got something. So this is what Hans Bethe in 1939 published. His concept was, now you can't really make two hydrogen nuclei stick, and nobody could, because the major thing is what I just described was the creation of the deuterium nucleus utilizing the weak nuclear force interaction, which creates the anti-electron and the neutrino. So everybody else prior to his work had been saying, well, how can we force the two protons to stay together? And Hans Bethe said, no, how about the first thing we do is once they stick, that instantiates the weak nuclear force, and that makes it turn into a neutron. So now the hydrogen, the new deuterium nucleus can now collide and do other things. And we had this whole series of steps. And there's Hans Bethe really smiling because when he did this, he received the Nobel Prize for his advancement in physics. I believe it was 1967 is when he was awarded that prize. I imagine this is his picture from that time. So what did he call? He called it the proton-proton chain. So the first step is you take two protons and smack them together to form a heavy hydrogen, which is a deuterium nucleus. And one of the pieces of output is an E+, or that is a positron or an anti-electron. And that mu sub E is an electron neutrino, or a neutrino associated with an electron. So that is the first step of the reaction. So basically this is a reaction chain. And so you take a proton and proton, smack them together, that's what the arrow indicates, and you get out a deuterium nucleus and a neutrino. And the neutrino indicates that the weak nuclear force has come into play. The gamma ray, the neutrino itself then becomes, of course, we just described how the neutrino, it leaves the town, but the anti-electron merges with electrons that happen to be around and becomes a number. It smacks into an electron and becomes a gamma ray photon. All right. So now the next step is, because the proton is now shielded, the deuterium nucleus is a proton and a neutron. That shields some of the positive charge of the proton in the deuterium nucleus. So almost immediately the proton and the deuterium nucleus collide because, well, it can kind of come in from the backside and smack the deuterium nucleus where the neutron is, and that forms light helium. So and then emits a gamma ray. So we can think of the helium nucleus as a light helium nucleus with two protons. That's what He stands for, which is helium nucleus. But it's got three particles in its nucleus, and so two protons and a neutron. But when it's created what we could call hot, and it's a resonant frequency, so it can absorb it at those temperatures. And basically it's created in an excited state, a nuclear excited state, and that allows it to emit a gamma ray. So it's very similar to the creating an excited state of an atom, like in the Bohr model, except there's no little orbits inside of a nucleus of an atom, of atomic nuclei. So there's just an excited state, and it emits a gamma ray. So now we've got two gamma rays being emitted, one from the first step and now one from the second step, and each of these things has to happen twice. So now we have four gamma rays being created. And then finally, we have the two light helium nuclei smacked together because now they can do that. But you have to have very high temperatures because there's positive charges, right? 4 positive charges have got to overcome it. And this is where the 10 million Kelvin thing comes into play. So now they've got to smack into each other. They form a helium nucleus, and the kinetic energy that comes out of them it releases 2 of the protons. They fall out of the nucleus. And you're left with a normal helium nucleus plus 2 protons coming out. So the only thing that we get out of here is we basically take the top 2 lines, do that twice, and you end up with the bottom line. So 6 protons go in, and 2 protons, and a helium nucleus comes out. So the net result is 4 protons in, 1 helium nucleus out, and some other stuff like light, anti-electrons, and neutrinos. That's the end result of the proton-proton chain, and that's what earned Hans Bethe the Nobel Prize. This proton-proton chain occurs about 10 to the 38th times every second in the core of the sun, and those times you see inside this diagram show roughly the average time it takes between an interaction. So it's very rare for the first step to happen. It's extraordinarily easy for the second step to happen, and it's not as hard for the third step to happen, but it happens pretty quick. This process every second converts about 4 times 10 to the 38th protons into helium nuclei every second, which means that about 6 times 10 to the 11th, or 600 billion kilograms of hydrogen is converted into pure energy every second. That's interesting. That's really interesting. That works out to be about 4 million metric tons, and that's, or 100 billion megatons of TNT. That's a lot. So this is an enormous amount of energy. This process can actually duplicate the output of the sun, which is about 4 times 10 to the 26th watts, which is an enormous, enormous amount of energy. So that's how we know that what's going on in the center of the sun. So we can take this theoretical construct and see how much energy is in there. And we say, does this really happen? And how big a volume is this happening in? We say, okay, the size of the core of the sun, I mean, that sounds like a lot, right? 10 times 10 to the 38th times each second. That's a big number. 10 to the 38th is big, but it's spread out. So if we then say how much it's being done over the volume of the core of the sun, it's pretty crazy. You say, well, how much power is being produced in the volume of the sun? You say the total power output works out to be about 275 or 276 watts per cubic meter. Okay, what's 276 watts per cubic meter? That's like 300 watt light bulbs in a large U-Haul box. So that's not a lot of power, actually, per cubic meter. And that's about the metabolism of a lizard. So it's kind of funny. The total output of the sun in the core, averaged out over the volume of the core, is really, 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 really small. That makes it kind of fun. So the tremendous power output is because the sun is enormously large, not because it's providing a lot of power. So the volume in which this can occur is enormous. But if we then think about what this is like, the largest nuclear explosion ever done by humanity was in 1961. It was the Tsar Bomba that was detonated by the Soviet Union in 1961. They were originally going to do a 100 megaton nuclear blast. They made it 50 because they were scared. And that is basically 1% of what happens in the sun's core for 39 nanoseconds. That's crazy. So the blast caused huge damage up 600 miles away. It could be seen the blast was felt 1,000 miles away. Every second the sun does this 100 billion times. That's an enormous output of energy, and it's very good that the United States and Soviet Union and everybody's trying to dial down the nuclear bombs because they destroy lots of things, and it's better to be alive than dead. Thank you for not blowing those up over everything, guys. So the proton-proton chain is a way of actually so the mass difference is extraordinarily small. Is that enough to make the sun shine for a very, very long time? The mass difference is tiny. That's called the binding energy of the nucleus. It's a tiny amount of energy that's released, and there's a huge amount that's happening. But is that enough energy to make the sun last long? So let's actually analyze it. Oh, but first, there's another process that we can use called the CNO cycle, which uses carbon, nitrogen, and oxygen as a catalyst. I'll let you pause this and go over it if you wish to. But essentially, that stars like the sun don't do this. The sun only does this for a little bit of it. But if for stars that are just a bit more massive, it accounts for a huge amount of the process of the sun. The proton-proton chain is for stars like the mass of the sun or smaller. And any stars that are even slightly more massive than the sun, this is the dominant path for fusion. In any event, so the lifetime of the sun, how much gets converted? So it's 0.7% of the material gets converted into energy. So if we took the entire mass of the sun and converted it into energy and divided by its luminosity, that would give us about 100 billion years, which is interesting. But the sun will only participate because it's not convective down at the core, it's radiative down at the core, because we know that from stellar structure equations, that so only 10% of the mass of the sun participates in this. So since only 10% of the mass of the sun participates in this thing, then it reduces to about 10 billion years, and boom, there we have it. The total age of the sun can be about 10 billion years, and the age of the Earth fits into that. And we know the age of the Earth from meteorites and from other things to be about 4.5 billion years. So therefore, but the total age of the sun is much longer than the age of the Earth, and boom, we've got it. Nature, therefore, is revealed to us as us mere mortals, because it's just an amazing amount of stuff. 4 million tons of matter is converted into energy every second. Is turned into energy, completely gone. The mass becomes energy. And so modern estimates of radioactive dating give about 4.6 billion years. If we look at meteorites such as calcium aluminum inclusions inside of meteorites that fall, specifically one of the great falls that happened in 1968, called the Allende meteorite, which happened in Mexico. That meteorite fall gave us huge amounts of data about the age of the solar system, and we now know the age of the solar system is about 4.567 billion years old, and that gives us a good time. So the age of the solar system is about half the total fusion lifetime of the sun, so therefore the sun can live for about 5 billion more years. So stars shine because they're hot, and to stay hot, they make up for the energy lost. They have to make it up for it. And there's two ways. First, the gravitational contraction, which still does occur, but nuclear fusion keeps it hotter because now we have a pathway in order to get energy out of the sun. And that nuclear fusion solves the age problem that came up with in the middle of the 19th century and would have made Lord Kelvin shake his head. That's what we've got, the age of the sun. And let's see, so main sequence stars, we discussed this before. Wow, we talked, what are main sequence stars? Well, like the sun, they rely on the proton-proton chain, but more massive stars with much higher core temperatures do the CNO cycle. Here's an interesting question, though. Why doesn't the sun explode? Well, the fusion reactions are extraordinarily temperature dependent. And so think about it this way. If you increase the temperature of the core, well, the nuclei move faster. If they move faster, then they stretch into the Gamow Peak. The peak goes faster, which means that they quantum tunnel more frequently. If they quantum tunnel more frequently, fusion occurs more frequently. So if you have higher temperature, you have more fusion. But fusion, as we know, creates light. And if it creates light, it creates energy. And that energy then goes into making the core hotter. So if it's going hotter, that should lead to even more fusion. So why don't stars explode? Like big bombs. Why don't they go out of control? That's an interesting question. So there's a thermostat. Again, we go back to hydrostatic and thermodynamic equilibrium, and we say when the core heats up, that leads to a higher pressure. The higher pressure means that the whole core expands against gravity, and that cools the core, which then slows the rate of fusion. Now, if it runs a little slow because stuff's running out or what have you, the core cools, which leads to a lower pressure. Then all of a sudden gravity pulls things together, pulls it, makes it contract, and then that heats the core. Ideal gas law again, because PV nRT, right? So the total amount of material gets compressed, and if it gets compressed, it heats more, contraction heats it, and increases the rate of fusion. That's a thermostat. That makes it so it cannot be a runaway explosion. So it doesn't happen. Also, it's a fact that quantum tunneling is extraordinarily rare to begin with, so actually getting the first reaction is rare, so you really have to push very hard. But the dominant thing is the hydrostatic thermostat, because the core of the sun can actually respond to pressure waves due to like waves of pressure that happen on top of it. And that's a rather rapid process. So in sum, energy is generated by nuclear fusion in the core. So it's controlled by a hydrostatic thermostat and regulated by the advancement of the quantum tunneling, which is actually what allows to occur. So the energy is then transported to the surface by convection and radiation processes in normal stars, and we haven't talked about white dwarfs yet, but we will, and you can go Google around if you wish. But the energy generation is called thermal equilibrium. Energy is created, it makes its way to the surface, it's radiated, so more energy must be created. because it's being radiated. And then hydrostatic equilibrium says things aren't sloshing around really hard, or more specifically, hydrostatic equilibrium says if you decrease the pressure, you compress. If you increase the temperature, you expand, and so you decrease your temperature. So these two sets of equilibria merge together, utilizing the energy sources of nuclear fusion and to some tiny extent gravitational collapse in order to generate energy in the star, in our sun. So that's how the sun shines. The sun shines through fusion in the core, and it can live for 10 billion years, not 6,000, 10 billion years before it runs out. Fascinating stuff. And that shows, and all of these things are basics of modern physics. And that makes the sun a core area where we can study and test the nature and understanding of particle physics as well. Next time we'll see exactly how that went haywire just a little bit. So, see you soon.